horrible at physics.
Really?
This is so unfair.
That's fine. Listen, let's try not to create friction as we play this game.
No, you took my point. I was waiting.
At least you tried, and that's all that.
Listen, guys, after you bring static friction, make it easier.
Yes, true. Yes, you just gotta get it moving. So let's see if as long as your group can get at 1 point and start moving, it will get easier after that.
Wish us luck.
The question is, do you have enough force to break static friction? Alright, we're already telecasting. Just waiting for them to show up. So, okay. Those of you who couldn't be here today, make sure that you follow along with us. If you actually, turn in the work here, there's too much light. Let me see if turning off the lights will help. Hold on.
Do we press the button?
No, let's close this first blind over here. Yes, you buzz in. You buzz it in to answer the question.
Can we use this?
Let's see, we're doing laws of motion, 78. There's so much here that we can do. We're gonna stay. This is gonna take a couple of days to get through.
90 better.
78. What the hell, man? There we go. 78. Except 78 is not really 78. All right.
79.
Net force.
NT5. Wait, do we just put like the first word? How do we number it again? I forgot.
You just write this, and then those numbers are going to keep changing. If you're at the beginning, but the last number, the 2, will keep changing. Okay. So you just write it at the top. This is NT5A-RT2. Okay. And then you're going to be RT3 and so forth. Actually, there must be a 1 then.
That's why I thought I was 7.
No, it starts with 2. Right. Now, here's the rules of the game. You get it wrong, you lose points. Okay? Everybody starts with 5 tokens. Everybody got 5 tokens. You got 5 chips. You get it wrong. It's a team effort this time. Okay. At the end, however many stacks of get, you're going to get that much in Legos. Alright? So, you're earning them together. So, whatever you earn, it goes for everybody. Okay? Now, here's the rule. If you buzz, you must answer the question. Okay? If you get it right, I might ask your group a follow-up question, in which case someone from your group, you guys confer and answer the question together. If I'm trying to say? So, if you buzz in, the person that buzzes in must answer the question without the help of the other people in the group. Are you with me? Mm-hmm. Now, if that person answers incorrectly, and somebody else answers correctly, then the point comes, instead of from me, from the bank, it comes from that group. Mm-hmm. So that's how that works. So it's kind of like set up like the brain bowl. So the way it works is, so if you get it wrong, right, and then as soon as I say, no, that's wrong, somebody else can buzz in. If they buzz in and they get it right, then the point comes from you, not from the bank. Is that clear? Yeah. If on the other hand you get it right, you get a point. And then if you get it right, I sometimes will ask a bonus question, but you can get a second point. For the bonus question, you can confer as a group and decide which one is the right answer. You guys got it? At the same time, keep a individual record of it to turn in for points as well. Okay? So you get points at the end. All right. Answer the question. Let's go for it.
Can I press the button if I know the answer?
Mm-hmm. First person for first. It's not about.
Can I work for it after I press the button?
Yeah. But the explain the reasoning is the bonus. It's the follow-up. So all you need is the answer. Are you with me? If you get it right, then you guys can confer and do the explain the reasoning thing.
Wait, do we discuss them on our groups now?
No. Okay. No discussion until the first person gets the answer. Then you hit it, and then if you get it right, your group has a chance of talking about the bonus.
And we get it wrong, we lose.
Somebody else can buzz in and try to get it right. Yeah, no, but if nobody gets it right, then you don't lose points, right? You only lose a point to the group if,
Well,
we'll find out. It's a bit hard to see on the video. I'm going to try to bring it closer. I want to know how to take this out of here. I don't like that about. I'm going to get that out of there. Page navigation. Rotate view, no. Read mode. There you go. Video phone screen. But that needs to be closer though. All right, online people, this is the best I could do. It's not very clear. I need to buy the software to make this high definition. Without high definition, the numbers are too jumbled. But we'll talk about it so you guys can get a chance. No one's asking for this. Come on.
I don't remember if it's the
All right, what's up with this?
The net force is 0 because you're not accelerating in any direction.
Well, that's not what you're supposed to do. You're supposed to rank them.
Or the net force is 0 for the cards. You're not accelerating in any direction. They give you a vector velocity.
Technically, but if you draw, wait, can I talk?
Hold on. You just answer, by the way, the question. You don't explain it. Okay? You should just say what you pick.
Okay.
All right? Just say, the net force is 0 for 5 vouchers. You follow that up with the explanation already, which is the fact that if they're moving across velocity, then there's no force. Right? Yes, you're right. There is no net force. Give him from the bank. Okay, so then, can we have a little bank next to you guys there? Grab a few of them. Grab a few of them. And make sure, obviously, don't steal. Guys, watch them. Don't let them steal from the bank. Okay? Put them away from them on the corner of the table. All right? Can't trust under this. All right. But yes, he's right. And the follow-up point is right as well. Get another one. Get another one to your stack. Why? Because what is the definition of inertia, of being in an inertial state?
no acceleration, constant velocity.
No, constant velocity, or just staying stopped if you were stopped. All these things are moving across velocity, right? So these are velocity vectors, not acceleration vectors. Are you with me? Remember, writing down individual answers is also a point for yourself, regardless of what's happening to your group. So you try to answer yourself, and then if you get it wrong, you got to call a pen to fix yourself. But you must try to answer it, right? These are counting against you. All right, so let's do the next one. Oh, this is 4. What happened to 3? It's too slow.
What is this?
I guess it jumps from 2 to 4.
So we just put 4.
All right, here we go.
We put 4 on it.
Uh-huh. Remember, the first person to have it, buzz it in. The figures below show 6 identically curling stones that play the playing pieces on a sport of curling. They are pushed horizontally along the ice by the thrower. For each stone, the instantaneous velocity and acceleration is given. The positive direction is to the right, and we assume there's no friction on the ice. First one has velocity of 3 and acceleration of 1, then 2 and 2, 5 and 1, 3 and 2, 2 and 1, 5 and 2. And the question is, rank these stones on the basis of the magnitude of the force that the thrower is exerting on them at the instant shown. So these early ones are easy. We got to get through them fast, all right, so that we can, these are super easy. You should be buzzing like almost immediately. Yes, Andres.
So D equals F equals B.
Don't explain. Remember that, right?
Okay. Greater than.
No, so you're saying D equals F? All right.
D equals F equals B.
Okay.
Greater than A equals C equals E.
Very good. All right, that is the answer. How could you tell that was the answer?
Because they only give you the acceleration.
And they're all the same identical stones. Now, that's actually important. If the stones have different mass, would that matter? Yeah, because acceleration is force divided by mass. And they're asking about the force, right? But since they all have the same mass, you can directly relate acceleration to force. Are you with me? Okay. Everybody clear on that? So make sure you have the explanation for that, by the way. You're explaining that since they all have the same mass, you can compare their forces directly from the acceleration. It's kind of like you're looking at F equals ma, and they're asking about the force. M is the same for all of them, so all it's going to matter is the A. Are you with me? So, and that's how you do it. Okay. 6. It's skipping. Is it stick it?
Yeah, it's going on evens.
Get out of this screen and see if that's something that's I'm doing wrong.
No, it's on 9. That's an odd number.
4.
6.
Even 6. Okay, fine. I guess it doesn't have it. Okay, that's fine. I'll put full screen again. Full screen. Control L. Wrong direction.
Oh, let's see.
Sorry, having technical difficulties. We're doing 6, right?
Yeah.
One step down. Alright, here we go. A tugboat. Each of the 6 figures below show a system containing of a tugboat pushing 2 barges, which are labeled 1 and 2. 1 is always on the left. The mass of the tugboats and the barges along the acceleration of the systems is given for each case. The positive direction is to the right. Ignore the effects of fluid friction. Alright, so there's no friction between the boats and the surface. Alright, so that's a lot of information they're giving you guys here. So they give you the mass of the tugboat in all the cases. They also give you the mass of each of the barges and the acceleration that the whole system is going into. Right? So 8,000, 6,000, 7,000, 6, 8, 6. Those are the masses of the tugboats. We have 1,500, 2,000, 2,500, 1,500, 2,500, and 2,000 kilograms for that. We have 1.2, 1.2, 1.2, 1.5, 1.5, and 1 for the acceleration. And then the masses are 2,500, 2,000, 1,500, 2,500, 1,500, and 2,000. So they switch things around. Lots switching around. This time we're looking again for the force that a tugboat exerts on the barge 1. Okay? I remember how last class we talked about the whole hammer problem and how it's different to push something light first than pushing the heavy one first. Remember that? So that's what they're asking you. They're asking about the force that the boat is exerting on the thing. There. You have to try to rank that. It's a little difficult, but not that difficult. There needs to be some calculations going on over here. But you can do it conceptually as well. When we're doing ranking tasks, what's the secret of these? You get the first one, and you create a basis, and then you compare the second one to that one, and the third one to that one, right? So you give this a score. So this is my A value. Is this half of A, 2 twice A? Are you with me? And that's how the best way to do it is like that. So in this example, mass 1 is lighter than mass 2. Well, this example, mass 1 has the same mass as mass 2, and they have the same acceleration. On this example, again, they have the same acceleration, but this time mass 1 is heavier. So they're just, you don't even need to calculate things. You just have to think about it. This one is heavier than this one same weight, and this one, that one's heavier, right? So lighter, heavier, same, heavier, lighter. Then everything's the same on the bottom, except this time it's going faster, or accelerating faster, right? So when you compare this to this one, it's the same situation, but it's way faster. But then they also change the mass of the tugboat, right? And so forth. No guesses yet. I feel very manipulated. You guys have to do the process more, guys. I mean, it might not work if the king keeps playing the game here.
I should have buzzed for number 4, man.
All right. So, what do you think?
Okay, so I think it's D equals E greater than A equals B equals C greater than F.
All right. Let's see your justification for this. Okay.
It wasn't supposed to be, you ask one person the thing and then the follow-up question goes to the group?
Right. So you guys, but I honestly want to hear your justification for this.
Okay.
It's that bad.
Is it that bad?
We'll see.
All right, so the way I see it, the mass of the tugboat doesn't really matter.
Absolutely.
Because
It's going to push it the same way every single time.
if you're already heading at that acceleration, that's just whatever.
Let's talk about that. Hang on. Let's talk about that. There's a learning here. Okay. This tugboat is pushing this thing to the right, which means they get pushed back this way too. Now, the tugboat is just the thing that's exerting the force, right? Whatever the mass of the tugboat is, it's going to exert an X force, which is going to make the things all move in that acceleration. Technically, you can think of it as the acceleration. The tugboat needs to move itself too, though, right? So technically, that acceleration, the summation of forces equals ma, right? So the acceleration of the system comes from the force that the tugboat is exerting, the total force the tugboat exerts, divided by the total mass of the system, right? So just let me go slowly so you guys, those of you who are lost, you can learn something from that. And we'll go back to that in a second. What did you say again?
Okay, it was D equals E
D equals E,
greater than A equals B
A equals
C
B,
greater than F.
equals C, greater than F. We'll see. Now, there's easier ways to think about it. He probably thought about it that way, but let's actually break it down and learn some dynamics. Okay, so then, what is the total force? We don't really know, but we know the total mass of the system. So look at this. This is 4,000. This is what? 8,000. Now look at this one. That's what? 12,000 again. And then that one's what? No. Look at the mass of the system we're looking at. Okay? Good morning. All right? This is 8,000 plus what? Plus 4,000? So that's the total mass of the system here. Total mass of the system. It's 12K. Right? What about total mass of the system here? 10K. What about the total mass of the system here? 11K. What about total mass of the system here? 10K. What about here? 12, yeah. Okay. And what about here? 10K. So that's something that matters. Why? Because the force, the mass of tugboats and the barges along with the acceleration of the systems are given for each case. Now, they're giving you A, and they're giving you M of the system. Correct? Because, so from that you can find the force the tugboat exerts. The total force the tugboat exerts. Right? So if you wanted to do that, we could. So let me just, as an example, the first one would be 12K divided by 1.2, which would be what? The force that it can do then. Come on, 12 divided by 1.2? 10K.
No, it's times.
Now we're trying to find, force, you're right. So it would be 12 times 12, right? So it would be 144K, right? Are you with me? That's situation A. That's the force that the tugboat has, right? Let's look at situation B. It's this times this, right? So it will be what? 12K? No, it's K is the 1,000. It's just 10 to the 10. You know, I'm just saying I'm trying to put a, K newtons, kilonewtons, right? You can think of it that way. All right, so then, put a little K. Okay, what about here? what? 11 times 12? 144 is 12 times 12, right? So 11 would be 144 minus 12, which is 132. So surface relation 3 has 13.2 kilonewtons. Okay. Now you see the bolts. That's the first thing that matters. They're not pushing you with the same strength. Are you with me? Because it has to push itself and the others. The mass of the boat, tugboat, does matter, because how much force it can push depends on it itself as well, because it has to push its own weight, right? So for the entire system to move at that speed, you have to include the mass of the boat on how much force it's going to have. Now let's talk about the contact forces, and that's something very important that we have to learn about in this topic in general. It's going to be important later. This is a review of something we talked about last class. If we have a force acting here, and this is 2m, and that's m. So we have a heavier thing going first, right? Of that force, if you think of now, we start talking about this contact force that exists between the two of them there, right? This, and let's say this whole thing is going with an acceleration a to the side, right? That force has to be equal to 3ma, right? But off that 3ma, how much has to push this guy? Just ma, right? Because if you look at just the acceleration of that guy, so this is the force that acts on the system. If you think about the force that acts on object B, it's just going to be ma, its mass times the acceleration of the system. Now, it's clear that the entire system has to have the same acceleration, just like you see in the problems there. But as you can see, the contact force here that's pushing it is just ma, right? On another example, when they have the same mass, right? So let's see how the forces compare in this case. By the way, if this is ma and the total force of the system is 3ma, that means, you know, it's almost as if 2ma of that force is what's pushing a. And then it's not exactly like that because it's pushing the whole thing, right? But that contact force only needs to be ma, right? In this particular example, right, we have on two objects, it would just be ma again, but the force of the system would be 2ma, but the force or the contact force would just be ma again. Now, when you put the smaller one and then the big one, the force of the system still has to be 3ma. So you see, it makes no difference for the system in which order you put the masses. You're still going to push the same mass, the same acceleration, right? But remember, in this problem, it's not the same acceleration for everything because you have to push different things. Even looking here, right? This is 4,000, that's 4,000, that's 4,000. Yes, the mass you're pushing is always 4,000, but it has to also push itself. We'll talk about that in a second. So for the total system, it matters the mass of the thing. But let's see if it matters for the contact force that we're asking about. If this was m and this was 2m, right? So then, like we talked about this last time. This time, the contact, if you talk about the acceleration of the system, if it's a, the total is 3ma. Thinking about this thing, the acceleration of object 2, it has to be 2ma because its mass is 2m and the acceleration of the system is a. Meaning that when you push on a smaller object into a bigger object, or a bigger, more massive object, not the size, the mass, right? You're going to have to push, the contact force is going to have to be a lot bigger, right? So, with that in mind, right? If you're thinking about the total force in the system, on these examples, in every single case that you're pushing it, right? You're always pushing the same total mass up ahead of that. Like, you see, in this example, you're pushing 4,000, 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 right? So there is no difference in how much mass is being pushed ahead of the tugboat, right? In all cases, the tugboat, so let's call this 4,000 mass that has to be moved, let's call that m. So in every case, this tugboat is pushing m, right? But in some cases, it's pushing the m faster. So in the bottom here, it's pushing m faster, which means that force has to be bigger. Are you with me? Because it will be pushing it at a higher acceleration, that same mass. So now we're talking about not the force that's pushing the whole system. I'm just talking about the force that acts from here forward, that contact force, right? So it has to be just the m, as in 4k newtons, right? Times the acceleration that it is. So that means that in every case here, that force, by the same token that we did over here, how did I figure out how much force was needed to push that little guy there? Well, I thought about it. It's its mass times the acceleration that it's going. So that's a blanket rule that's important. How do I figure out the contact force needed to push that thing forward? You just look at what mass is ahead of that, right? Times the acceleration. So in this case, the mass that's ahead of this contact force is what? 2m times a. That's why you call it 2ma. So in these cases, it'll be the same rule. You're going to look at the total mass that's ahead of it times the a, right? I went into this because I just wanted to make sure you guys understand that to push the entire system, the tugboat may need more force. But look at this. In every case, the mass ahead of it is 4 tons, right? So the only thing that matters then to figure out that force that's pushing it here is F equals ma, where m is the mass ahead and a is the acceleration that the mass ahead is going, which in this case has to be acceleration of the whole, right? So in this case, it will be 4,000 times 1.2. In this case, it will be 4,000 times 1.2. In this case, it will be 4,000 times 1.2. Are you with me? I'm trying to say, which means all of the top ones have the same contact force, right? So why is it the force of each one of the total is different? Because the mass of the tugboat is different. But that contact force is pushing it can't be different because in every case, ahead of that force, the same amount of mass is being pushed. Are you with me? So, just in case you got confused again, when I'm trying to figure out the contact force that needs to happen, it's almost like I pretend that it's not in there. And that this stuff has to move with that A, right? And since this as a group, as a system, they all have the same 4,000, it's just 4,000 times the A. Which means all the bottom ones will go first, and all the top ones will go next. So, not like that at all, right? But you said A, B, and C would be the same, right? So in that sense, you were right, okay? You said D and E would be the same. In that sense, it was right. So I was like, oh my God, who's going to get this right? Because you actually have everything out except for F. But F has 1.0. I didn't see that until now.
Yeah.
All right. So it's actually right. Yes. So I thought that was 1.5, but it's not. It's actually 1. Which means now he actually had to hide it one more time. All right. So it's good to be his team. Maybe he should play alone. All right. So he doesn't need help. Okay. But anyways, is everybody clear that to figure out the force that's pushing something, I just have to look at the total mass of that and the total acceleration of that, right? So if let me say they were asking, let's change the question, okay? So you can practice this concept. Let's say they were asking about the second contact force, right? Same problem, but the second contact force. Remember, if I want to know the second contact force, I just look at this doesn't exist, right? And then whatever force that is has to be pushing that mass that's ahead of it, right? So in this case, it would be this times this. In this case, it would be this times this. In this case, it would be this times this. So it would be this bigger than this, bigger than this. Are you with me? And then you just have to do that for all of them. F equals ma. It's literally all you need to know for this topic, other than F equals un for the friction, right? And F equals kx. The rest is just applying that concept. So make sure you guys are clear on that. That was a good one. Review a bunch of stuff. All right, let's do some graphing stuff. Graphs show up on the AP test all the time. So I love that they have that in here. So what do we have here? What is this graph representing? Look at it carefully. Force applied over a period of time. Now we're thinking about acceleration. Okay? So let's do this is actually a really good momentum problem. And I'll tell you why in a second. We're going to teach you something I literally heard ahead of time, but this matters. We didn't really talk about the second law. It did not. It's this whole A equals F over M is not a Newtonian concept. He never, well, he is, but that's not how he presented his rule, right? It's actually completely different. Maybe we can rephrase this in a few ways, all right? What is A? What is A? Delta V over delta T, right? Which equals F over M. Are you with me? Now I'm going to switch things around and look at this. M delta V equals F times delta T. Are you with me there? This right here is called momentum. And that right here is called impulse. Okay? Or actually this is called change in momentum. And that's called impulse. Right? The force that you apply over a period of time. It's called impulse. So this is actually called the impulse momentum equation. But you see how it's a derivation that comes from equals MA in kinematics? Right? So remember this now. I'm going to come back to this later in the year. But when you put kinematics with time, so kinematics with time inside of F equals MA, you get momentum. When you put kinematics with space inside of F equals MA, you get energetics. And you're going to find out that every single problem you can do in kinematics, you can do with dynamics plus momentum or dynamics plus energetics. And it's actually sometimes easier to do it this way than to think of it in terms of kinematics problems. That's if you're doing the math part stuff. But conceptually, that's not what we're doing about. Let's go back to the question. Let me go back to this step right here, where we're talking about that, and then divide both sides by time. Right? Now remember, well, this was momentum, right? So we'll call it momentum like this. And then force is basically the rate at which momentum changes. That's Newton's second law. All right? Basically, force is the rate at which the quantity of motion of something changes, because that's what momentum is. Momentum is the quantity of motion. Right? So then basically, force is the rate at which an object changes its quantity of motion. All right? Now, what this means, though, right, is that if you get, what can you tell from this graph? Well, let's think about area under the curve. Remember those things that we talked about? Every time you have a graph in physics, like this, when they put a graph like that, make this rule. I'm going to figure out what the axis is, what the area and the slope means. Sometimes it has no meaning, but sometimes it does. Let's think about the slope here. Rise over run. There will be change in force over change in time. Is there a meaning for that? Force divided by time? Not really. Okay? But force times time, what is that? We have a meaning for that, which is what? Momentum. Right? So what is the area under this curve? The change in momentum. Is that clear of the object? Remember that later. We're going to bring this back later. But what do you get if you get the change in momentum, which is this thing, and you divide it by mass? Look at it. All right? Because let's go backwards. Let's redo the change in momentum. You go back over here, right? So if you have changing momentum, so that would be what? This equals the change in momentum. So, but if you divide it by mass, you can just get change in velocity. Are you with me what I'm saying? Now, therefore, if you think about this graph and whatever change in momentum you find, so if I got the area under the curve, and I divide by that by mass, I'll find out how much the velocity changed over a certain period of, and then I have the time in the graph too, I can figure out acceleration. This is actually very important. This graph shows up a lot in the test. Let me go down again. The area under the curve we decided was change in momentum, right? Which is something we're going to bring it back later. But if I divide both sides by time, I get force. But that's not what I'm talking about. If I got the area, the change in momentum, and divide it by mass, I get change in velocity, right? And then if I see from the graph how much time passed for that, I can get what? Acceleration. So it's a really roundabout way of looking at it, but let's think about it. The bigger this area is, the more change in momentum that is. All right? So when I increase this area over here, the area in the curve, the change in momentum also increases. And now let's think about this. If I have a positive area, what does that mean about the momentum? It's going up, which means velocity is going up for a certain mass. Are you with me? Okay? So the bigger the area, the bigger the velocity change over a certain period of time. So the bigger the area, the bigger the acceleration. Does that make sense? Make sure you guys remember this, write this shit down, it's important, right? So, let's, one more time so you understand. What is the area that here, how did I figure it out? Because it was force times time, and we had that equation, right? Now, if we divide by the mass, so if you know the mass of the object that's doing this, right? Then we have change in velocity, right? So if you divide both sides by mass, we just have change in velocity, right? But since we know the period of time over which that happens, we can get acceleration. So in an indirect way, the area under the curve here, the size of it, means how much impulse was made. And the bigger the impulse, the bigger the change in acceleration is going to be, right? The bigger acceleration is going to be for a given mass, right? So, they ask you to rank the acceleration of the cars in the times listed below, right? So, yeah, it's not that hard. It's really not. So, what is it? Rank the acceleration of the car in the times labeled below.
Yeah.
Where's times 1? I don't even see it. Where's number 1?
It doesn't have.
I don't even see the numbers.
1 is at the.
Oh, these dots over here. Okay, that's for the.
And you missed the F dot.
Yeah.
It's right there. It's pretty noticeable though.
Oh, there's something else that we could learn from the graph. There is a meaning. Force divided by time. Hold on a second before I move on from this. If we do force divided by time, just 1 second. For a given mass, though, would that give me acceleration? If I know the mass, making sure of something. Because obviously this problem is talking about the slope. I mean, I only see area be useful here, but they're comparing slopes here. They're not comparing areas, right? Because it's at that point. What is the acceleration like? Right? And it's the slope of it. But I've never seen about like. Somebody Google up the meaning of the slope of the force versus time graph. Meaning of the slope of force and time graph. Because the thing is that when I look at it, the slope is just force. Yes, but give me 1 second. Force divided by time. I don't know if that means anything. It would just be this divided by time. Or the rate at which acceleration is changing. The rate at which acceleration is changing. Jerk.
I don't think there's asking us that.
That's what the slope means. The slope means jerk.
I don't think the slope matters, is what I'm saying. I think what matters is where the point is.
That's it.
In the y-axis.
It's really not that complicated.
Because where I did was
Oh, the actual value of the force.
Yeah.
Because for a certain, of course, there you're right. It's not the slope we're looking at. We're looking for the value of f, right? So you want to say that?
I have an
Okay,
answer.
fine.
It's
So
a
tell me your answer.
C is greater than B equals D. When you want to write it, or you want to write it?
That's fine.
Okay, C is greater than B equals D, greater than F, greater than A equals E.
Right.
I missed your whole explanation. I don't even know what you said.
No, it's fine. No, it's cool. We actually learned a lot of things from that. So we learned that the slope could give us information about the change in velocity. But
I had a different explanation.
but either way, this graph is telling us directly the value of force. You can say the back.
Can I give my explanation?
mass is
What are you here for?
Can I give
Yeah,
my
the mass is the same, it's the same part.
For the what?
I just made the mass.
What about it?
The mass was one.
I did the collage. There's a picture of it, but I'm not sure if you wanted to actually use one.
Just leave it and leave it on the back over there, and I'll take a look at it
Can I
later.
give my explanation?
All right. Okay. No, it's okay. This.
I
That's
can get a
8.
tip, right?
Hold on.
I can get a tip?
I want to, yes, and the explanation as well. If you give it to me in a second.
Yeah.
Now, I know I went to the direction that's now that we needed for the question, but let's review what I talked about because this is actually important stuff. From the area under the curve, you learn something about the change in velocity the object is going through. You learn about the change in momentum the object is going through. From the slope, you learn something about jerk. And from the actual value of f for any given m, you can actually figure out the acceleration. With me? So if I'm giving this graph, there's 3 things I can tell you. 1, the jerk. That's the slope. It's never going to be useful in this class, right? the second thing you can learn is from the value of F. If you know the M, you can figure out A, right? Because A equals F over M. So if the M is not changing and it is the same mass doing all of this, right? Then from any given value of F, you can get A. And from the area, you can get the change in velocity or change in momentum. Is that clear? So I review those three things. It's important. Make sure you remember it. Guys, take notes on this stuff, okay? Because it's, later on we're going to go over this again. So she said this was the biggest acceleration because it has the biggest magnitude of the force, right? And it's positive.
Because the equation is A equals F over M, and then
right.
they all have the same M, whichever has the biggest
right. Exactly. Now, whenever we're asking about the magnitude of the acceleration, then you have to be careful. Just remember that. If let's say this line went all the way down, right? Then that would be actually a bigger magnitude.
Yeah.
Are you with me? Because the force will be bigger, just the direction is really different. So just watching out for that, making sure you release that. Okay, let's keep going. Okay, it's okay. We take tangents, but we do some learning in the process. So now when we read the chapter momentum, you won't be completely lost. Anyways.
No, I got one already.
Let's go.
Oh, you get another one for the explanation?
Yes.
Just two? Oh, okay.
So now, guys, it's F equals KX in the business here. F equals KX. We're going to need that. Let's go. The figures below show systems containing blocks which are initially at rest in a frictional surface. In each system, the block is attached to the end of the spring, which is stretched to the right. You can stop me if you get the answer before I finish reading. The mass and spring constant are given in each case, as well as the distance that the spring is stretched. So basically, they're giving you M, K, and X, right? When the mass is released, the spring will accelerate the block, right? You kind of expect that. You're compressing it. The spring is going to want to, right? Okay. So, and they actually want you to know the acceleration of that thing. Okay? Yeah, we're going to compress it, let go, and they want you to know the acceleration. So, we got 5, this is the spring constants. Okay, and we got 5, 5, 4, 4, 1, 1. Over here we have the masses. We got 1, 1, 2, 5, 5, 4. And then we have the compression, which is 0.4, 0.2, 0.2, 0.5, 0.5, and 0.5. We have F equals MA and F equals KX. Alright? This is a general equation that we can use in dynamics. That's an equation that applies to the force in the problem. And they want you to solve for A. Right? It's not a difficult question. Remember, conceptually, even when it's conceptual, you go to the formulas, identify the formula that helps you, and then it solves the problem. It's actually easy. Okay? And remember, when it's a ranking problem, you give this thing a score, and you compare the score of the next one with it, and so forth. It's the easiest way to do it. Buzz in when you're ready. Well, let's try not to get Andres to get the point again. Just buzz.
No. Hold on.
You're going to lose 1 point.
I know, but
You don't get any by not trying.
I think I'm really wrong about this. Hold on.
That's right. You'll always miss 100% of the shots you don't take. And that way, we just let Andres be the king. Come on, Derek. You got this.
Yeah, Derek, go for it. I'm positive I'm wrong.
You can go right ahead.
Go, just try it.
I'm wrong.
Derek, have faith.
Fine.
It's just a game.
Have faith.
It's just a game. You're getting Legos for it. Who cares?
I'm worried.
I don't have faith, Shannon.
Come on. I'm disappointed. I'm disappointed. You're too slow for this. Okay, hold on. Let's see if you got it right, first of all. A
is greater than B.
Okay.
Greater than E equals D. Is
Uh-huh.
greater than C. Is
Uh-huh.
greater than F.
That's your guess?
Yes.
All right.
Is that right?
All right. Let's see. How did you arrive at this? What is it with the formulas?
To find a solution, it's
Yes.
force over K.
It would be force over M will be the acceleration. But what's the force?
KX.
KX. Right? So in each situation, you just got to give the values, and then that's it. So let's compare A with this one. They have the same constant, so that it won't matter. But A has double the compression, right? But then this thing also has double the mass. So that means A has to tie B. So that already makes your answer wrong. All right?
I was wrong.
Right? So
Wait, but see, I was wrong.
Yeah, I was wrong too.
are you with me what I'm saying though?
Yeah.
Remember how I did this? Hey, pay attention. How to do the ranking test. You work on the first one, that's your base, that's A. I'm going to compare B with A once I have a formula. Okay, hold on. The force is Kx, but force equals A, so you can set them equal to each other. Right? Which means A is Kx over M. Now, this, you don't need to plug in numbers and get numbers. You just think about what they're doing and compare. So think about it. The same K, that's not going to affect anything. You're doubling the compression, so there's twice as much on top, right? But you're also doubling the mass at the bottom. Think about it. Oops, I think I made a mistake.
Yeah.
Because you're doubling this one, and then you're halving on the bottom if you compare it to that one. So it's actually 4 times as much. A is bigger than B. So you were right. I am so sorry.
Yay.
Okay. By the way, if I'm giving this a score, then there would be a quarter of A. Would that be right? A quarter of A? Because it's half of X and double the M?
Yes, it's a quarter of it.
So it will be a quarter of A. Alright, what about the next one? Let's try to think about it. Now, this makes it half on top, right? But now you're increasing the bottom by a little bit, and you're also decreasing K a little bit. So it's going to be smaller than A, right? And you have to look at the numbers though to compare to this one. That's the thing. Usually they make it easier than this, but this time it wasn't that easy. In this case, I think it would be easy to plug them in, right? Instead of doing comparatively like that. So it would be 0.1 times that, which is 0.5. Is that what you guys got from that?
I got 0.5 for B. A
And this would be
0.16.
0.16, which means this beats it. So B is bigger than C.
Yeah.
So far, Derek is doing pretty good. I'm sorry, Derek. I made a mistake. I'm sorry. In fact, you get a double bonus because of my mistake. All right? So then, what about here? We got 1.5 divided by 1. It's 0.5. It has to be equal to D.
Mr. Lima,
Look at him go.
I have it
Mr.
here.
Lima,
Yes?
you made a mistake while I was
Did
while I
I?
was answering. Yeah.
Yeah?
You didn't see the 1.0.
That's an E, Lima, not a C.
That is true, I do. Get an extra one for me.
Lima, that's an E, not a C. Lima,
Huh?
resubmit my answer. That an E or
That's C.
No, here. What you roll on the first
That's E?
E. Yes.
Oh, so he was wrong.
I know,
There
but
goes
I
Derek's
have the
answer.
right one here. I
Alright.
trusted him.
And then the C, let's look at E. That would be 2 divided by 4. So it's
Is
0.5.
another 0.5. And
So it's another equal.
yes.
Oh, he's not wrong yet.
C doesn't equal D though.
Of course it does.
No.
No,
C
you got
is
0.16 0.5.
It's A is greater than B is equal to D is equal to E.
Oh, he is right. That's the second mistake I make.
We must not make mistakes, man.
Sorry.
B is equal to D.
Is
B is
he?
equal to, yes. B is equal to D is equal to E.
Oh, so he did make a mistake.
Yes.
Okay.
So what's up?
They are equal in the middle.
Tell him that.
Alright, and this would be 0.5 or 0.5, which is 0.1 times 1, which is 0.1. So it is the worst one. Oh, it was so close there. Should we give Derek the point anyways?
Yeah.
No, we
I
shouldn't.
trusted you.
We shouldn't.
He's gonna be the king soon.
You can have 1 because she had it right, but not 2. Okay. Alright, let's keep going. Open the door, someone, please. Judah wants to come back in.
It's locked.
Guys, make sure you keep rackets for yourself because it's a point. Let's keep going. 13. Oh, that's an easy one. It's based on something we already talked about. Alright? Remember,
Oh, I suck at tangent.
it's not about that. Remember the rule I told you about? You're going to do the total M that that force is acting on times the total A. Alright? Now, in any system, the A always has to be the same. So, all of the blocks have 2A here. All the blocks have A here. Right? But this tension here has to pull what? 2 MA. Right? If they're the same blocks. That tension has to pull what? 3 MA. That tension has to pull what? 1 MA. Because it's just what's the mass that is acting on. Right? The total system would be 3 MA. Right? Right? But this would be 2 MA, that would be 1 MA. Right? So it's easy. What about this one? 2 MA. Well, actually, it's 2A now. So it's 4 MA. And this would be 2 MA. Are you with me what I'm trying to say? So this will be what? 4 MA. This would be what?
Yeah.
So, I know, sometimes I'll do it. Right? This will be what? 2 MA. This will be what? MA. This will be 2 MA. This will be 3 MA. And that is 3 MA. Which puts A equals D. No, B,
is greater than A.
which is greater than A and D.
D, which is greater than C, which equals E, which is greater than A.
Exactly. Now, you guys understand that's an easy one. From now on, don't get these wrong. Anytime there's tension or contact forces, just think about what's being pushed and what's being pulled. So when you're trying to think of this tension, you pretend the rest doesn't exist, right? And the A has to be the same A as the entire system. Therefore, that has to be MA, right? And if it was pushing, it's the same thing. So let me give an example. If I was pushing from here instead, what would be the force?
That'd be
3 MA. But if I was pushing from here, and I was pushing from here, I understand what I'm saying? Okay. Make sure you explain that to get the point. All right. Don't worry about that one. Oh no, that's actually good. Let's use that. But I'll do this one myself. Okay, now look at this. Use the velocity vector to find the approximate direction of the acceleration of the system. Think about it. If I pick a place right here, where would be his velocity vector be pointing? At that point. The direction that the hill had at that point. Right? What about here? Where would it be pointing? The same tangent again. What about here? Where would it be pointing? The same tangent again. Are you with me? Now, what is acceleration? Acceleration is that change in velocity over the change in time, which therefore is derived as velocity final minus velocity initial over time. Except these things are vectors. So we have to have vector addition. So velocity initial has to be flipped, right? And then I have to add them together. That's how it works, right? A negative, so I have to add this to this one. So if I'm adding them together, then I have to put this one right here. Oh, remember how you do this? You put this one right here. And then this right there is your direction of the acceleration. And where is it pointing? To the middle of that big circle. Right? That's how you derive centripetal acceleration. We're going to talk more about this when we do curve, the motion course. Right? So we'll bring this back. We'll bring this back when we're talking about thing. But if you're drawing a free body diagram, that we should be able to do. Go ahead and do that, please. First correct free body diagram gets points. Let's do it. That should be easy. I gave you one of the accelerations, one of the forces already. What is that force? It's called the guy to turn in a circle. It has to be called centripetal force. Okay? So we didn't learn about that yet, but remember, the force that makes something go towards the circle is called what? Force centripetal. Right? What is the force centripetal this time? In general, that's what's called, but it's always something. And when you're throwing up, it's tension when you're wrangling a thing. With gravity, can be the one that causes orbits. And in this case, what is the force centripetal? The normal force. Very good. But is that the only force that's acting on it? What else should be acting on it here? Weight. But weight comes in what direction? This direction. But you could, instead, you could do what? Instead of weight, you could also split it and have a weight X and a weight Y. You can do one way or the other, but not both. Right? Okay. So that would be it. I'm sorry that I took the point away. I'm trying to catch up on the time. All right. All right, this is quick. I just taught you this, and I told you don't get this wrong anymore. So let's try it. Drop your pencils when you're ready, or be the first one to buzz in. Extra. The tensions. Compare A and B tension. It's super easy based on what we talked about. They have the same acceleration. No, same force, sorry. All right, so what do you got?
The tension in B is greater than the tension in A.
Okay, and why?
Because the mass that B is pulling is greater than the mass that A is pulling.
Well, but you have to look at the total acceleration first. Right? Because remember, F?
The same acceleration.
How can you tell? Because it's the same force acting on 3M. Right? I'm just making sure you knew that. Because your explanation has to be thorough. If you just said, A is pulling in a bigger mass. Well, but what if this thing was going What if this thing was going much slower? Much, much slower. Are you with me? So B is greater because it is pulling a bigger mass, but it's only greater because it's pulling a bigger mass at the same acceleration as A is pulling. And how did you know it was the same acceleration? Because the same force was acting the same system mass. Is that clear? Make sure you write these down if you want to get points. Look, so how would a total, complete explanation answer here sound like? So like, yeah, 2. So how would a total, complete explanation sound like here? Let's put it together. B is greater than A, right? Because it's pulling what? More mass at the same acceleration as A is pulling, right? You can determine that acceleration is the same by looking at the fact that the same force is acting on both systems and that both systems have the same total mass. You see how many elements you have to have there to have the complete answer? Otherwise, you miss the big picture, right? Make sure of that. Guys, make a habit out of explaining everything. Oh, I love these. This is awesome. It's a classic thing. Now it's getting interesting. I don't know. The computer's retarded. Now it's like 3 questions ahead. I don't know. It's like going... I think so. What just happened?
Wait, why was there 14 if there wasn't 15?
Ooh. This is going to get good. My next class is going to get real good.
We're going to do this in class too?
For sure.
Okay.
I'm confused. What did I do? Oh my gosh. I went like to the hill. Oh my gosh. No. Just no. Yeah, I went to circle of motion by accident. We were like on 78 and all of a sudden we went through 100.
There.
It's right here, right?
Yes,
Or
that was
No.
one. Yeah, that was
18.
Yeah.
Okay, go.
Oh, then you have to make this quick together.
I love it. Not for the game. Just answer it, drop your pencils when you're ready. Okay? Actually write it down. I want you to practice this thing about explaining. Practice it. Now that it's not an FRQ. Which we may have one next time. Definitely going to have one next time. Well, then it is. Practice it. Practice this. FRQ practices online. Right? Practice it. Don't come here without practicing. Look at the practice.
This doesn't count for its points to give.
No. But I'm really interested in your explanations. So, it's not that bad. Sometimes it is obvious, and sometimes it's not as obvious as you think. A continuous string that's ideal has the same tension throughout it. You guys know this, right? So, if you guys wrote something, you didn't write anything. Why are you having so much trouble? What do you think the tension on the string is? Do a free body diagram for this object. Start there. Do it right now. Right here. Right there. Do a free body diagram for that point. Right? The force that you think is pulling it down, the force you think is pulling it up. So what is that free body diagram going to teach you about the tension? Must be what? No. The tension, if you did this right, you should have tension and the weight, which is 1,200 newtons, right? So what does that mean about the tension here?
It's the same.
All right, so what's the tension here? It's going to be 1,200 newtons, right? So, can she lift it?
Oh, no, because
It'll lift her
She can.
Why?
because the object has more inertia.
But it says that she can weigh, she can
Yeah,
lift
but
1,600.
she weighs 800 newtons.
But she's capable of lifting twice her weight.
Yeah, she's capable of lifting it. Wait, is it asking if she'll be able to pull it?
Yeah.
Yeah.
Well, she can't pull it because the object's inertia is higher than... The object applies an opposite and equal force in her direction, so she'll get pulled more than the object.
But she can apply
She can-
1,600 newtons of
So
force.
she can pull it. There's nothing wrong with her can.
See, so sometimes the answer really is obvious.
Exactly.
You just need to think about it. Like, if I can exert twice more weight, more force than the weight of the object, I should be able to lift it. No problem. That's simple. Now, because it's not about acceleration, it's about force here, right? Can she exert more force than the force she needs to lift it? Yes. So you complicated yourself by, oh, but let me think about inertia and the mass of the woman and the mass of the pail and all that
But
stuff.
it's asking if she can pull it.
Not everything's a trick
Yeah.
question.
Not everything's a quick question. She's just asking if they can lift it. Can she lift it? She wants to lift the object, right? And it says she can lift twice her weight. So she
Yeah,
is.
She can lift twice her weight. She can pull twice her weight.
Same thing, bro.
It's the same thing.
It is.
Yeah.
Stop trying to find loopholes.
You're right that it's not exactly the same thing,
Yeah, but she can.
but that's what it means.
I actually have no idea what just happened.
You're wrong.
They are
every
trying.
time
Okay,
today.
if you're taking like a gym lingo, yes, it probably doesn't mean. That's not the same muscles.
Okay.
But what they mean is that she's capable. She has enough strength to handle 1,600 newtons.
Right.
Yeah,
but-
she's so as fuck.
She's not. That's not how. Oh, she's sold as fuck. Never mind.
Yeah.
That's 1,600.
She weighs
That's.
way less.
Huh?
Doesn't matter.
Yeah, but okay, I weigh less, but I can pull more.
Yeah.
Exactly.
You can-
When people go to the gym, they can.
Yeah, you work out and you pull 200 pounds, man.
Exactly.
You don't have to weigh 200.
Like, bro, it
You don't have
doesn't
to wait,
matter.
yeah.
Yeah,
For
if you're
real.
fixed to something.
Not really. You could just be standing there and pull it.
Of course you can.
Slow like.
They can.
What do you mean you can't? How the hell do people drag airplanes in their back?
Exactly.
That's all you do. You can pull it. That's how
Dude,
people do it.
Okay.
If you weigh 100 pounds, that thing weighs 200 pounds, but you can pull
You can lift
300.
it. You
Pretty
can
sure
lift
pull
it. Go to the gym.
I don't know why you're having trouble with this one.
I actually
Sometimes
don't
you don't have to
know.
break-
All right, the moment she touches it, right?
Yeah.
She has the strength to pull it. It has nothing to do with her weight. Nothing to do with her weight.
Exactly.
If she didn't have the strength, because think about it, her weight is holding her down. In fact, she can pull 3 of these pails, 2 of these pails. I'll tell you why she can pull 2 of these pails. Because she weighs 800. So that means the net, let's say she doesn't do any force, she just holds it like that. Yes, then the net force will be 400 up.
If she's pulling, she's using
Right?
force.
But she also has 1,600 on top of that of what she can pull. So she has her weight, or she has 1,600. Are you with me? No, she can't use both things at the same time.
Well,
Think about it. No, she can't. How are you going to hold 1,600 and just use your weight and pull at the same time? You can't do that. You can pull if the friction on the floor is there, right? So, you know what I'm saying? So she has the strength to pull, or she can use her weight. Now, we're not talking about her using only her weight. Of course, you're right. If it was her weight, she would be flying the other direction, right? But she can pull twice her weight.
He looks so amazed.
I don't understand why.
It's because he's too smart. He's too
Smart.
smart.
You can't just have
All right, let's do it. Velocity versus time. What is the slope of this graph telling us? Okay. All right. So a student asked how the net force acting on the engine of graph A at identify point compares to the net force on part B. And then he says, I think B has a larger net force since the net force on A at the identified point is 0. What, if anything, is wrong with this statement? If the statement is correct, you have to explain, right? Yes.
I think both net forces, it's wrong because both net forces are the same.
Yes,
Both
why?
Constant velocity.
What?
Constant velocity book.
Oh, they're not constant velocity. You had a good, and then you lost me.
Wait.
How is this constant velocity? This is graphing velocity. It's changing over time.
Okay.
What's
I mean,
constant?
No acceleration.
The acceleration is constant.
Exactly, but no acceleration means no net force.
Well, there's acceleration.
Huh?
It's changing velocity. So there's acceleration. Yes, there is.
Oh, that's
This is
right.
velocity. Velocity is changing.
Right.
But how is it changing? The slope is it different from both graphs? You can look at it. Is it different? No. So if the slope is the same, acceleration is the same. Acceleration is the same, the mass is the same, force is the same. Are you with me? So they have, but there's a lot of things which are wrong. It says he's saying the net force is 0 at that point. Is that right?
No.
This is not graphing force.
It's graphing velocity.
This is graphing velocity. So he's already wrong right there. Okay. And then B is also not graphing force. So are you with me? So the first mistake he's made is like you don't even realize what this graph is. But you can actually say something about the force, right? You can say it's the same because you can tell from the graph's slope that the acceleration. Are you with me what I'm trying to say? You guys have to try practicing voicing all these things that I'm saying. Practice that, guys. Practice that because that's what the FRQ is like. We talked about this in class, about how it becomes easier or harder to lift something if it's talking about friction. But they're not talking about friction here. They're just talking about the force that's acting on the object. Okay? So, in both cases, the angle is the same. In one case, the force is applied downwards to the object, and the other force, is pulling it. And they say, will the magnitude of the force on the block by the stick in case will be greater than, less than, or equal to the tension of the block in B? So, the magnitude of the force on the block by the stick. They have the same acceleration, right? Buzz when you're ready. Yes?
Okay, I think the magnitude of the force on the stick is greater than
This one? So that one will be greater than this? Is that you buzzing?
Yeah. It's me buzzing with my elbow.
Alright, and what do you think? He's wrong,
There's
yes.
no force.
Huh?
There's no force.
He's wrong too. There's
The net
force.
force is 0. The net force is
No, it's not. It's like, oh,
constant
yeah.
velocity.
It's no force. He's right. Right. Because it's constant velocity. So we know what, but that's not what they're asking. No, that's why I'm saying you're wrong about your answer.
Okay.
They're asking what's the force. You're right. There's no net force. How could you tell that there was no force? That's force.
It's not accelerating.
No accelerated. But that's not what they're asking. They're not asking about the net force. They're asking about the force of the tension. Versus, by the way, how can there be no net force here? What else must be present? Friction. Friction must be there, otherwise this thing will be accelerated, right? Now, in which case is friction bigger? This is important too.
the first one.
Right, because it's going to be
Yeah.
pushing on it, which means
Right.
friction will be bigger, right? And in this case, friction is what? Less,
Right, it's being lifted.
because it's being lifted.
That's why I got it. So I'm right technically, but not really. I guess. Sort of, in a way.
So let's think about it in terms of vectors. This has a large, so a small friction vector, right? Which this thing must match, right? And then there's a certain amount of y component which is whatever.
Yeah.
This vector, and then the angle is the same, right? But in this case, the friction is bigger, and then this force has to have that bigger component to match that. But then what about the y vector?
It's the same. The equals the same. No, it's negative.
No. In this case, because remember, that you're right, that this x component of that force will be different. But why are you assuming that this x component is the same? Because it's true. I'm just making sure that you're thought about everything. Because remember, when you're explaining it, you have to think about everything. Yes, the x component of this thing is definitely, because the friction, you can tell because it's being pushed, the x component is different. But what about the y component?
This is hard, man.
It's not that hard.
It's negative, but it's the same magnitude.
Okay. How do you know it's the same magnitude?
Because it's the same angle, the same.
You don't know the angle.
Oh, what did you say?
You go home, study this.
I know, it's hard. But it's not that hard. Look, I'm just making sure we're not assuming anything here. Because, yes, you can see why this x has to be smaller, because I'm finding less friction, right? But I had to do, to achieve that task, I had to pull it up,
Okay.
right? In here, I pull down on it, which is what causes me to have more friction, which means this becomes bigger.
What do you mean?
It's a trade-off. Yes, you're getting a smaller x here, but because you had a bigger y.
Wait, so then I was.
I hate
Are you with me? You have a smaller x, but because you're pulling it up, so you have to exert more y to get a smaller x, right? In this case, you have a smaller x. Yes, because bigger x,
Bigger, yeah.
right? Because
Push it down.
it has to fight that friction. But what do you know about the y? You have to make sure that it's different or the same. Because in order to just basically assume that the force will be different, you have to say the y is the same in both cases. Does the y have to be the same in both cases? Well, the angle is the same, for which the force is applied. But it doesn't mean the guy could be pushing more or pushing less on the other case.
So what you have, so it's two right here.
So for the y to be the same, the force has to be the same. They need to tell you that the force and the tension are the same.
I just don't. I'm thinking. I'm not saying I'm right about it, but I'm thinking. Okay, let's think about it in terms of MA or whatever. Let's give this M because I'm actually having trouble. That's why I'm trying to think about it.
It is hard.
No, I'm not having trouble. Like I'm saying, like you have. There's a lot to think about here. Let's say think about the normal force. Okay, so the normal force here has to counteract the part of the weight that's up here, because there's actually a force for Fy up here. There's a normal force, and then there's the weight. We see that? Now, so weight is mg. So I'm doing a dynamics equation for this, right? Normal force plus Fy, which is tension. Y, which is tension times the sine of that angle, right? Minus the weight, mg, equals 0. That's what I know about that direction. Now, I can also write down, therefore, that the normal force is mg minus t sine of the angle, right? Which means the friction is going to be u times mg negative t sine of the angle in this example here, right? And that is what the tx component has to be equal, right? Because in the x direction, all I have is f of the x and the friction. With me? If I'm doing a free body diagram. So that means that is what tx is composed of, right? So if I'm trying to solve for t, total t, right? What would that be? Well, this is tx. So how do I go from tx to t? Remember, t times cosine of the angle equals tx. Therefore, if I'm going to get t, that's tx divided by cosine of the angle. So that means this t is going to be the tx, which is this, right? So it's mu mg u mg minus t sine of theta over cosine of the angle. And that is what the tension is. All right? Are you with me so far? That's the first one. Let's think about the second one now. All right? Same thing. So let me erase all this stuff, and we can think about it. Same thing. He has a weight pushing down, right? He has a normal force pushing up, but he also has a force pushing down, which is a force y, right? There's a force pushing this way, which we call a force x, and an equal friction pushing this way, right? So let's do a y direction diagram. That would be Newton normal force minus weight, which is just mg, right? Minus f of x, which is just basically f times the cosine of the angle. Okay? Not sine of the angle. The sine of the angle will give you the vertical component. Right? Which, if I'm going to solve for normal force, that means it's equal to mg plus f sine of the angle. So unlike this case where the normal force is mg minus, in this case here is mg plus. Are you with me? So then, f on the other direction, we have Fx equals the force of friction. But the force of friction is mu times m, which is that thing right there. Therefore, U times mg plus F sine of the angle.
That would be
Okay.
TB.
No, that would be Fx. So likewise, before, to actually get F, I have to do Fx over cosine of the angle, which therefore would be equal to U mg plus F sine of the angle divided by cosine of theta. The angle is the same in both cases, so these terms won't matter. M and a G are the same in both cases, so the terms don't matter. The mu is the same in both cases, so that doesn't matter. So all that matters is in this one you're adding, and in that one you're subtracting. So that means this number is bigger. That one's bigger.
That's what I said.
Okay, but you have to explain that. So,
I got one ship.
I'm just going to make sure you understood it. That's all. So why is it bigger? Because you are fighting more friction to pull it, and there's no difference in the y component apparently. But without proof, mathematical proof, you don't learn it. Now, in this process, we actually learn how to do, again, free body diagrams and dynamics equations, and how they solve it for you. Now, I know I went through it pretty fast, but you got to watch videos. If you don't, you get lost on this. How did I do this? I made the free body diagram for both directions. Technically, I'm supposed to do that on a point, but I was working on it fast, right? If you're doing it on the test, you put a point and then do it. You think about all the forces going up and all the forces going down. And then what I did here? Normal force is up, so I call it positive. Negative, negative, right? Equals 0, by the way, because it's not moving in that direction. And then I solve for the normal force, because I needed that for finding the friction. I told you guys this on the video that I recorded just the other day and last class, which is in a lot of these friction problems, you need the y direction to get the normal force, which you need to get to the friction. Because friction has the normal force in it, and that's a y direction thing. So you use the y direction equations, which are these right here, right, to find your x direction equation, right? So in the x, why did I put this equals this? Because the actual x direction equation is fx minus friction equals 0, because there's no net force going across the velocity, right? And then I reworked in that and so forth. Make sure you follow. If you got confused, it's recording, so make sure you do that. One more. You're right. But the thing about being right is that to truly gain the points in the test, it's not even about being right. That's one point. Where you got the most points is explaining it. And without this kind of proof, right, you don't have an explanation. So you could say, oh, it's because it has to fight a bigger friction, but then you don't explain why is the y component different, right? So you can see the x component has to be bigger. We already knew that conceptually.
Yeah.
But if you do the y component, think about it. Ty equals t times sine of theta, right? And the same thing will be on the case. It will be f times sine of theta. And we found what this will be. So it would just be this times the sine of theta, right? So all that would add to this is basically to get ty, it will just this be times the sine of theta, which will be tangent of theta. Are you with me? So in both cases, it will be tangent of theta, but it will still be negative and positive, right? So there is a difference in the y component as well. And in both cases, you need more force in both directions to get that result happening. All right, velocity versus time. We already did this, but they also give us force versus time, and they want us to graph from one to the other. All right, so let's look at this. What's happened to the velocity at first? What does the slope of this tell us? Acceleration. But if the acceleration is negative, what does that mean about the force? It's also negative. Now remember how I told you that the change in velocity that we get, right, can be inferred from this graph? From the area under the curve? Remember that? So you could actually, if you had the mass, you could actually get numbers for this. But what's going to be happening to the velocity? The force is decreasing or increasing here? Let's think about it. Is this acceleration changing? No. So what does that mean about the force? Is it changing? No. So, but it's negative. So what does it mean about the force? Negative. So we need to have something negative like this, right?
Yep.
Right. And then what happens there? What does that mean about acceleration?
0.
Okay. And then what happens next? But look at the slope. Positive. So it has to be a lot more positive, right? A lot more than the other one, in fact. Okay? So, right? And then after that,
It goes back to 0.
why? Because it's not accelerating. That was an easy one. Remember how in the last FRQ there were problems like this? You have to transform one graph to the other?
We don't need to connect
So-
the line.
Now you have to, you shouldn't, because it jumps magically, right? So you don't have to do vertical things. Now, explain how you can figure this out. We just thought about it because it's decelerating, therefore it has to have a negative force. But in this, it's accelerating, so it has to have a positive force. But it has to be a much more positive force than that one was, right? Because the slope is bigger, which means acceleration is the magnitude. The magnitude is bigger. All right? And the last one today. This is vectors. We already did this stuff, so we're going to skip it. All right. Similar to the ones we did before. A ship is pulling 2 pods. We're talking about the magnitude of tension at point P. See this P right here? Remember how we solved this problem? We just ignore everything else and look at the point at what's being pulled. Are you with me? So none of this exists. Are you with me? So what is the situation here? The pod is accelerating that way at 2 meters per second, and we have a mass of 2m. So you can think of it as 4m meters per second squared. Right? Oh, sorry, the force, 4m newtons. Whatever m is. Right? What about this example here? It's got a mass of m accelerating this way. Right? So what does that mean? A will be bigger or smaller. It's m, guys. But it's,
Oh, it's M.
so it's 3m newtons. But what about the fact that this one's going the other way? We'll talk about this next time.
Yeah, because it's going to be...
It doesn't matter because it's on the other side of it.
So B is greater than A.
No.
Huh? We'll talk about this next time. At point P, huh?
This is a lab from my kinematics from a while back. Do I put it in my number or do I give it to you?
Are we trying to send?
Sorry?
It's a lab from...
Just give it to me.
Well, we just did turn it in.
Hold on to it because we're going to do more next time. Okay?
Can I turn in the correction?
Yes, please. Don't forget that last time's corrections for last time's quiz, whether you were here or not, are points that I'm expecting.